Welcome back to Very Ordinary Differential Equations. In this video, we begin studying applications of first-order differential equations, specifically growth and decay models. Now, before starting a course in differential equations, just about any student is going to have seen something like the amount A of t of a substance at time t undergoing radioactive decay is given by the function A of t equals a sub 0 e to the kt, where a sub 0 is the starting amount of the material and k is some constant. Okay, this is a very, very typical way to phrase problems in, say, a pre-calculus course. But where does this equation actually come from? Okay, now manipulating equations and solving like, oh, if you begin with 50 grams and you have 30 grams after 5 minutes, what's K? That's old hat. You guys have done problems like that. So we're really not going to be doing examples in this video. We're just deriving where familiar functions are coming from. So let's suppose A of t is the amount of something at time t, a sub 0 is the amount at time t equals 0. Now this sounds like an initial value problem. A of 0 equals a sub 0. Suppose the rate of change is proportional to the amount. So the derivative of capital A is some constant times A. The rate of change of A is proportional to whatever A is. This scenario can describe several different types of things. Okay, bacterial growth that is unconstrained by food or space. 10 bacteria multiply a certain amount, 20 bacteria multiply twice as much, 100 bacteria multiply 10 times as much. The rate at which they are growing is proportional to how many there are. This is assuming that food never runs out and space is never an issue. Radioactive decay. Okay, if a certain percentage of your material decays in a given amount of time, that percentage is proportional to how much there is. Okay, if 1 kilogram loses 1 gram in a day, then 1,000 kilograms would lose 1,000 grams in a day. It's directly proportional to how much there is. Continuously compounding interest. You earn interest on the money proportional to how much money is in the account. Okay, they don't just give you $10 of interest, they give you a certain percentage. Now, what are the functions A that satisfy the differential equation above? A prime is a constant times A. So what we have is a linear first-order differential equation. A prime is a constant times A. This can be solved in a whole bunch of different ways. It's a separable equation, however, so we're going to do it that way because it's the easiest. We get A prime over A is the constant K. This can be integrated on both sides. We get the log of the absolute value of A is equal to KT plus some constant C. It's natural to assume that capital A of t is positive. The amount of stuff we have is not a negative quantity. In which case, you can exponentiate and drop the absolute value, and you get capital A of t is some constant times e to the kt, where our original constant lowercase c, e to that, is our new constant capital C. The initial value, however, was that a of 0 equals a sub 0. So if I plug in t equals 0 and I place over here a sub 0, we directly get that this constant c must be a sub 0. So there's the equation. A of t is a sub 0 e to the kt, derived very quickly from solving a linear first-order differential equation that was separable. But now let's try treating a model of simultaneous growth mixed with decay. Suppose, for example, that the amount A of t is affected by both of these things, growth and decay, where one is proportional to the amount, but the other is just a constant. Now our differential equation looks like this. There are two things contributing to the rate of change. One is K1A of t, proportional to the amount, but the other is just K2, a constant. For example, you might have interest accruing on an account. That's proportional to how much money is in the account. But maybe you're also contributing or withdrawing money at a fixed rate. So you might be earning 3.5% on your investment, but you need to withdraw $1,000 a month to cover some sort of expenses. So you've got interest proportional to amount and spending, which is constant. So you've got proportional growth, but constant decay. Or maybe rabbits breed in proportion to how many there are, but there's a fixed population of predators eating them. So their population grows proportional to how many there are, but decreases based at a fixed rate at which predators are eating them. Or perhaps you have radioactive isotopes. they decay in proportion to their amount, but maybe they're being created continuously at a constant rate according to some process. So something is creating radioactive isotopes at a fixed rate, and then they are decaying in proportion to how much there is. Maybe an object radiates heat proportional to its temperature, but energy is being generated by some process. So you've got heat being radiated proportional to the difference between two temperatures, but it's also being created at a constant rate by some other process. So how can we solve the differential equation that arises? We've got two factors contributing to growth. One is proportional to the amount and the other is constant. As given before, a prime is some constant times a plus another constant. If I rearrange terms, we get a prime minus k1a equals k2, and this is now very explicitly a linear first-order differential equation. But it's inhomogeneous. We have a forcing function of k2. So going all the way back to the second lesson, we know how to solve such things. First, solve the complementary homogeneous equation, a prime minus k1a equals 0. That's going to be separable. It's going to be solved by e to the k1t. Then, using variation of parameters, find a particular solution to the inhomogeneous equation. It's going to be of the form u e to the k1t, where u has to solve u prime equals the forcing function, k2, divided by the solution to the complementary equation, e to the k1t. Well, if u prime is k2 over e to the k1t, you can solve that to be u is equal to negative k2 e to the minus k1t all over k1. So I take this u and I multiply it by e to the k1t. It exactly cancels out this exponential. So the particular solution is just negative k2 over k1, just a constant. Note, if I have a constant, its derivative is 0. If I multiply this constant by negative k1, it exactly cancels out that denominator. I'm left with exactly k2. So indeed, the constant negative k2 over k1 is a solution. So since we have found a solution to the complementary homogeneous equation and one particular solution, we now have all solutions. It must be of the form, the particular solution minus k2 over k1, plus an unknown constant times a solution to the complementary homogeneous equation, e to the k1t. So this now describes all solutions to a prime equals k1a plus k2. The initial value, however, was that a of 0 equals a sub 0. Solving that for c is going to be a naught plus k2 over k1. So plugging that in for the value of c, we ultimately get this, negative k2 over k1 plus a naught plus k2 over k1 times e to the k1t. In some sources, if you look up these equations, you may have plus or minus signs in different places. These constants k1 and k2, I have not specified whether they're positive or negative. Sometimes it's important to consider, oh, this value of k must be positive, this one must be negative. And to clarify that, there may be pluses or minuses thrown around in the equations or in the functions. I haven't made the distinction, and therefore these k1s and k2s could be positive, could be negative, so it doesn't really matter where there's a plus or where there's a minus. The term steady state solution gets thrown around a whole lot in differential equations. Let's learn what it means. Now we solved our differential equation with this solution here. Suppose for the moment that k1 is negative. So up in this exponent, I have a negative number times t. If I take a limit as t goes to infinity, e to this negative number times t will go to 0. So this whole term vanishes and I just get the constant minus k2 over k1. But remember, k1 was assumed to be negative. So if k2 is positive, I now have negative, positive, negative. Overall, that's a positive limit. Suppose, for example, you have an amount of substance decaying exponentially, but being replenished at a positive constant rate. So k1 is negative and k2 is positive. Okay, then a of t, tending as t goes to infinity to this positive constant k2 over k1, tells me that value, minus k2 over k1, is where the two forces are exactly balanced. As time goes to infinity, the production at a rate of k2 will be exactly balanced by destruction at a rate of e to the k1t. Okay, and we have indeed found that this constant minus k2 over k1 does solve the differential equation. Furthermore, any solution will tend, as time goes to infinity, towards this constant. That's what we showed up here. As time goes to infinity, any solution will tend to this constant minus k2 over k1. So this constant solution somehow attracts other solutions. Any solution as time goes to infinity will tend towards that constant. So it's a constant which solves the differential equation, and any solution will tend to it with time. That's called a steady state solution. Now, both of the models we've discussed have some deficiencies. Okay, unconstrained growth has fairly obvious flaws. Okay, if it's growing at a positive exponential rate, as time goes, the population goes to infinity, and it doesn't really matter what you're modeling, infinite population is not really realistic. This mixed model, however, of exponential growth or decay combined with constant growth or decay can also have some flaws. If K1 is positive, the same issue actually comes up. So if something is being produced at a rate proportional to its size, you have a positive exponential here, and as time goes to infinity, that's going to escape to infinity as well. If K1 is positive, and this factor here is negative, then this amount goes to infinity times a negative number. So as time goes to infinity, your amount tends to minus infinity, which is even weirder. So the assumption that A prime is influenced by some constant K2 is actually not sensible for K2 negative if you also have A of t being negative. So when you have nothing, if A of t is less than or equal to 0, there's not anything you can take away from that. And the model we have just doesn't account for that either. But now let's suppose you want to model growth where the rate of change is actually proportional to two different things. It's positively growing proportional to the amount A, but it's negatively growing proportional to how close the population is to some constant K called the carrying capacity. So population grows, but as it approaches something K, there's another force that's going to slow down population growth. So we claim we can model this situation with the following differential equation. A prime is some constant times A times 1 minus A over capital K, where capital K was that carrying capacity, the limiting population. Well, where did this differential equation come from? So why does this differential equation model the situation where population grows proportional to the size, but limited by this carrying capacity K? For values of A that are very small, so suppose A is much, much smaller than K, then 1 minus A over K is basically 1, and you get the unconstrained growth of A prime as a constant times A. So if A is very small, you expect things to more or less grow exponentially. But if A is very close to K, well then, 1 minus A over K is practically 1 minus 1 or 0, so I get a 0 here. Then the K times A doesn't so much matter. If capital A is very close to K, I get A prime is very close to 0. In other words, the population growth is really slowing down. So here is our equation that we want to solve to model this situation. This equation is actually separable. Okay, A prime over A times 1 minus A over capital K is the constant K. So it is separable. Integrate both sides. Well, partial fraction decomposition and some algebra simplifies the left-hand side as presented. A prime over A minus A prime over K minus A equals the constant little k. So here's what we have after we did some separation of variables and partial fraction decomposition and some algebraic simplification. Well, these integrate respectively as log A minus log of capital K minus A, and on the right you get kt plus some constant c. I combine those two logs using properties of logarithms to be the log of the quotient. Now, I'm going to actually reciprocate A over K minus A into K minus A over A. That's just multiplying both sides by minus 1. If I multiply a minus 1 here and absorb it as a power, I can reciprocate what's inside the logarithm, and on the right, I just multiplied by minus 1. Now I exponentiate both sides, and we get capital K minus A over A equals e to the minus kt minus some constant c. So what we've got is capital K minus A over A in absolute value should be e to the minus kt minus c, and of course e to a constant can just be factored out as some constant c. So capital C is e to the minus lowercase c. Now we're modeling values of A presumably in between 0 and the carrying capacity. Okay, if we're modeling something that is in between 0 and the carrying capacity k, then both k minus A and A itself are not negative, so the absolute value is not necessary. And we drop that absolute value as such. Now we just need to solve for capital A. That was our whole goal. Well, it takes a little bit of algebra, but you can solve for capital A. It's k, the carrying capacity, over some constant capital C times e to the kt, where little k is some other constant, plus 1. So here is our solution. A of t is capital K over some constant c, e to the kt, plus 1. Now let's use our initial conditions. A of 0 equals A sub 0. That allows us to solve for c. It takes a little bit of work, but if you plug in a 0 for t, you get a 1 here, and A sub 0 there. You'll eventually solve for c as k minus A naught over A naught. I then take that value for c and plug it back in. Okay, plugging in k minus A naught over A naught for c, and then multiplying numerator and denominator by A naught to cancel out the denominator of c produces the following expression. A of t is the carrying capacity times the initial population over the difference between the two to the kt power plus the initial population A naught. This is known as the logistic equation. Okay, and again, you may have seen this before in a pre-calc class. Use the logistic equation to model something. What we've just done is show why the logistic equation looks the way it does. It's a differential equation that for small population values has unconstrained growth, but as you approach the carrying capacity, the rate of change, A prime, slows down to 0. And there's the solution, the logistic equation. All right, so what did we do? In situations where growth and decay is proportional to the amount of substance, okay, we generate linear first-order differential equations, and the solutions involve some sort of exponential term. We can modify these equations by introducing something like constant growth or decay, and still a solvable thing. And a particularly useful modification is to introduce a carrying capacity that as the population approaches, the rate of change slows down towards 0, and we were able to solve this to get the logistic equation.